Thanks, Craig. Thanks for the invitation. Just to say, for people who haven't met me, it's actually Helene, not Helen, but lots of people call me different things, so I answer to all any variation. So I was really lucky enough 4 or so years ago to be invited to be the coordinating lead author of the Ocean, Cryosphere and Sea Level Change chapter for the 6th assessment report, along with Baylor Fox Kemper and Kundi Shao. And I don't think I'd have at all realised at that time what a challenging task it was. And today I'm just going to talk about the sea level aspects of that. So I'll say a little bit about IPCC Working Group 1. I'll talk about the past sea level change. I'll focus a little bit more on the ice sheets, go on to talk about the projections to 2100, and then the change projected beyond 2100. And then I'll give you a bit of my perspective from COP26. Where I was part of the IPCC team presenting the results. So if you've got questions as we go along, put them in the chat. Craig's going to ask me them if you have them. Totally happy, whatever you want to ask, and I'll do my best to answer. So I'm sure many people have seen the report. So the outline of the Working Group 1 report was quite different this time to previous reports, largely sort of split into 3 themes. So first of all, large-scale climate change, a middle section all about climate processes, and then the final section going on to regional climate information, sort of like walking towards Working Group 2, if you like. And sea level information or assessments comes into many chapters. So I've highlighted just some of these: chapter 2, chapter 4 in the large scale, even chapter 7, because the equilibrium climate sensitivity is one of the things that feeds into the sea level projections. Obviously, at least a third of chapter 9 is dedicated to sea level. And then in chapter 12, it's discussed much more on the regional scale, and it's also included in the interactive atlas. So, what I'll show you comes not just from people working on chapter 9, but many people across the report. And so here are the people who worked on chapter 9, there's people working on oceans and cryosphere as well as sea level, but on many of the sea level issues, it was an assessment across the whole chapter. So many people had input to that. And we're especially grateful to the chapter scientists, particularly for the sea level, Tim Hermans and Greg Garner. And we had 74 contributing authors, many on sea level, and maybe many of you are here. And so, of course, particular thanks to Aimee and Bob, who did a lot of the work on sea level in the chapter. So one of the things that that seemed a little bit strange when we started off AR6 was that they'd just recently finished the special report on oceans and cryosphere in a changing climate. Well, actually, it hadn't finished. It hadn't been released when we started our work. So we were in this slightly odd situation. And, I did have times when I thought, well, what on earth are we going to do that's new relative to the special report? But actually, we actually did make major inroads. So we included new observations, particularly the IMBI updates. We integrated paleo into the multiple lines of evidence in the chapter, which kind of gave some greater process understanding. Relative to the special report, we moved things on towards CMIP6 models, particularly including Glacier MIP and ISMIP6. The methodology that we used, as you'll see, for sea level projections is quite different in this report. So we use emulators, we have consistency with other parts of the report. And of course, the projections are also based on the shared socioeconomic pathways rather than the RCPs of the SROC and AR5. So I'm sure people who have looked at the IPCC report or worked on it are really familiar with the uncertainty language, but it's particularly important in how we try and present the sea level projection. So I just thought I'd just talk about it again. So can you see my pointer there, Craig? Maybe.
Apologies, I cannot.
Yeah.
I'm afraid.
Oh, you
Whereabouts
can't.
is your pointer?
Okay, that's all right.
Oh no,
down
yes,
at the
I
bottom.
can. Yeah, we can.
Okay, good. Okay, so what we're looking at is we look at all the evidence, and we look at whether the evidence agrees, and whether we've got different types of evidence, how much evidence we've got, its quality and its consistency. And if you've got a robust evidence and it has high agreement, you'd say you had high confidence. If there was very little evidence or very little agreement between different strands of evidence, you would say you had low confidence. And so we try in the projections, as you'll see, we try and make this separation between things that we have at least medium confidence in, so in this area, and things that we have low confidence in, which might be characterized by deep uncertainty. When you have high confidence in something, then you can also go on to use these likelihood statements where they have very particular statistical meanings. So first of all, I'm sure everybody on this listening to this is familiar with a plot like this. If we look at how sea level has changed over the past 3,000 years, and this is shown again in chapter 2 of the report, is that global mean sea level has risen faster since 1900 than over any prior century in at least the last 3,000 years. And it's not just the amount it's risen; it's the fact that the rate is that the rise is actually accelerating. And acceleration is not a term that's used lightly at all in the report. I think sea level is the only place in the report where we actually refer to acceleration. But obviously, it's quite clear in terms of global mean sea level that we are seeing an acceleration. So at the beginning of the 1900s up to 1970, the rate was 1.3 millimeters per year approximately. That rose to about 1.9 from the 70s onwards, and in the last almost 20 years, it's approaching now 4 millimeters per year. So we're definitely seeing an acceleration here. In the report, we talk about the different. We try and look at these different drivers of sea level change. I'm mostly going to talk here about the global mean sea level, so the ice sheets, the glaciers, thermal expansion, and to a smaller extent the land water storage. But we'll touch on relative sea level change as well. So we have this really nice box in the chapter, box 9.1, where we look at the contributions both to the warming, so where all the heat has gone, and to sea level rise. And so when we look at just the sea level contributions, we can see that obviously back in the 70s, this was dominated by thermal expansion and the glaciers. Now there's a much larger contribution from the ice sheets. We talk in the summary for policymakers how glaciers and the ice sheets are now approaching being the dominant factor in recent sea level change. And we see that the Greenland and Antarctic ice sheets have increased by a factor of 4 from the 1990s to the 2010s.
Can I interrupt you 1 second? Sorry, we've got a question in the chat from Jeff. Jeff's asking, how much of the acceleration is due to increased observational sampling?
Well, that's a good question, but I think that I think that that was covered really in chapter 2, but maybe if I don't know whether Katia or Amy or Bob are on there, they could maybe comment on that. But I I think if that was the case, we would have pointed that out. That's not a very good answer, Jeff. Sorry. Is Jeff going to come back, Craig, or shall I carry on?
I think, yeah, it would be good to carry on.
Okay, so where do we get to? Okay, so ice sheets have become a big contribution. So I'll say a little bit about the ice sheets in particular. So we for the past, we looked at observations from a variety of sources, including the updated IMBY estimates, which Andy Shepherd and the team kindly produced for us. Those are now available. You can see them in the report. They have a DOI. We look at projections both from ISMIP6, which were emulated by Tamsin and co-authors in the 2021 paper. And we also have projections from the LARMIP2 simulations from Anders and co-authors. And we also consider projections beyond ISMIP6, including Ashvanden, Nick Golledge's work, etc. So if we just look at the past, so this is one of the figures from the chapter where we're looking at the change, the rate of change and the total change in the Greenland ice sheet. And so the headlines really is that the Greenland ice sheet has contributed 13.5 millimeters from 1992 to the present rate, and that rate is increasing. And the discharge and surface melt are both contributing, but the surface melt is increasingly dominating with high interannual variability, as you can see. So for the so what we've got here is this is now the scale is very different to what you've previously seen. So this is showing the change. So for the historical period, you can hardly see a change at all on this scale. And then you go into the future, and we're highlighting the 8.5 and 2.6 scenarios because those are the ones which were part of ISMIP6. And when we look at those projections here, these are the bars just on this right-hand side. You can see here, these are the ISMIP6 projections in the blue and the red with the mean and the distribution. And in Tamsin's paper, this was then emulated so that we covered all the different emission scenarios from 1.9 up to 8.5. And to capture more of the uncertainty. So, you know, the headline assessments were, not surprisingly, that the Greenland ice sheet is virtually certain to lose mass over the 21st century. We expect the surface melt to become increasingly important as the marine margins melt. As I said, we've emulated the ISMIP6 estimates to extend to the scenarios, to all the scenarios. And we also, you know, as part of our assessment, we assessed papers such as Ashvanden et al., which points to the possibility of higher loss, you know, because those are experiments which are outside the range of the ISMIP6 experiments. So similarly for Antarctica, we also looked at a range of observations. We had the extension from IMBY as well. So, you know, the headlines were that we had 7.4 millimeters of contributing to sea level coming from Antarctica from 1992 to 2020. That our assessment is that the mass loss from the outlet glaciers is outpacing the gain from snow accumulation, and high confidence that loss induced by basal melt and ice shelf disintegration is preceded by the surface melt. So if we look then into the future, and then it's slightly more complicated picture for Antarctica. Again, this is the past on a much bigger scale here, and this is projecting into the future. And you see with the average of the ISMIP-6 scenarios, there is much less difference now between 2.6 and 8.5. There's more spread in 8.5 if you look on these right bars than there is in 2.6. And so we emulate these to look at all the different scenarios. And we also look at the LARMIP2 emulation that Anders and others worked on. So our assessment overall was the Antarctic ice sheet is likely, so contrast that with Greenland, where we said virtually certain, it's likely to lose mass over the 21st century. And, but we're with more confidence that dynamic losses will outpace the accumulation. The ISMIP-6 estimates are emulated. Obviously, they show much less spread across the scenarios than we saw in for Greenland. There's more, I guess there isn't even a lot of spread perhaps in the LARMIP2, but you can see a greater, the distribution becomes wider for some of the higher emission scenarios. Tamsin and Anders can talk about this in more detail, but if you read in the chapter, you can see that the differences between ISMIP-6 and LARMIP can be explained by the range of basal melt sensitivity, which was used in those emulations, and that can bring the means close together. It still doesn't explain the increased spread that you see in LARMIP2 relative to ISMIP-6. And I don't think it'll be surprising to anybody that we said that there was deep uncertainty remaining around, particularly around the marine ice cliff instability, which obviously has potential to increase the mass loss from Antarctica. So I talked particularly with the differences between ISMIP-6 and LARMIP with the uncertainty in the basal melt fluxes. So in this figure, which we have in the paper, you see present day observational estimates of the basal melt flux, what this looked like in one of the ISMIP-6 parameterizations, what it looked like in FESM. And so you already see quite a reasonable spread in the present day. And then if you go into future projections to the end of the century, you can see that there's a large spread in these basal melt fluxes. So that's clearly something which deserves more attention moving forwards. And there's also considerable uncertainty, both in the more generally in the atmosphere and ocean forcing derived from CMIP-6 models, because it is these that are then used to force the ISMIP-6 projections. So I think there's a real opportunity here for, perhaps some of the modelling centres to look a bit harder at their both the atmosphere and the ocean forcing that's being applied over Antarctica. So obviously a big question that we were tasked with was looking at the thresholds for Greenland and Antarctica. And these are the summary statements that appear in the top level summary from chapter 9. And so what we say is that at sustained warming levels between 2 and 3 degrees, there's limited evidence that Greenland and West Antarctic ice sheets will be lost. But as the temperature warms, not surprisingly, we assess that the complete loss and the rate of mass loss will increase. If we move to higher warming levels between 3 and 5 degrees, over multiple millennia, we expect near complete loss of the Greenland ice sheet and complete loss of the West Antarctic ice sheet to occur, and the potential for substantial parts of East Antarctica to be lost. But again, we're talking over multiple millennia. So I think, these were the best statements we could make when we finalised the report last year. These are definitely things which the more we can pin these sort of statements down, the better. And I'll talk about that some more in the COP context. So moving on to talk about the sea level projections. So the methodology that is used for the sea level projections, as I said, has been updated relative to the 5th assessment report and the special report. We now use emulators. So we have the emulators of the contribution from the ocean derived from CMIP6, from the ice sheets and the glacier simulations derived from the Edwards et al. Emulator and LARMIP2 as well. So they use the equilibrium climate sensitivity and the surface temperature assessments in the emulators. So that means we have consistency across all the assessments in the report. So these are the main projections, and so this comes back to the medium confidence. So this, we believe, covers processes in which there is at least medium confidence. We recognise that there are also ice sheet processes in which we have low confidence in what will happen in the future. And so we characterise that as deep uncertainty or a low likelihood, high impact outcome. And I'll talk about that some more shortly. We also talk about sea level projections to 2300. And as I'll describe, these are based on the assessed literature. And because of the uncertainty really in the ice sheets, we've characterized these as low confidence. And just to say that the actual kind of framework for this will be is in something called FACS, which Bob Kopp and Greg Garner are hoping to be able to release at some point. And so hopefully this provides a framework which people can use to make future sea level projections or test some of the assumptions in there. So this is what the projections look like in the chapter. So if we're looking, so we went to 2100, that's where the CMIP6 models went to, and we extrapolated these out to 2150. So to 2050, there is, there's minimal dependence on the emissions scenario. We're largely committed to something between 16 and 27 centimetres of sea level rise. If we look beyond 2100, obviously the emissions pathway that we follow will make a large difference. So for example, by 2150, we're projecting that for the low emission scenario, which we call is what we call SSP 1 2.6, we're looking at between 46 centimeters and a meter. If we're looking at the high emission scenario by 2150, we're looking between a meter and 1.9 meters in the range. And then you see on this figure that we also mark this this low confidence, which is associated in this case with 8.5, and these are the high impact, low likelihood outcomes.
Can I interrupt you again 1 second?
Yeah, sure.
We have a question in the chat from Heiko. He's asking, how did you interpolate out to 2150?
Yeah, so we interpolated because we'd got the emulators, we were able to interpolate or extrapolate those. We have like relationships, and if you look in the table in the chapter, Heiko, which I can't remember the number of the table, it's all specified exactly in there. And so that's another reason why we want to release the FACS software so that people can exactly reproduce that. Hopefully that's okay, Heiko. If you can't find the table, I will tell you the exact number after the seminar. Okay, so before we looked at, I showed this figure, or at least the left-hand part of this figure, showing the rates of sea level change in the past. And so I just thought it's useful as well to put that in the context of the future. And so, we were looking at more recent periods of approaching 4 millimeters per year. The numbers for the end of around 2100, if we stayed at around 1.5 degrees, are kind of, you can see that the rate of increase of sea level is still about, could stay around 4 millimeters per year. If we go to much higher warming levels, you can see like these, you know, huge, relatively huge increases in sea level per year. And the reason that I think it's useful to present it like this is because, you know, post AR6, in fact, I've had, and I'll refer to it later, I've heard people say, oh, well, 3 degrees isn't so bad, but you know, we're not going to have that much sea level by 2100. But this would be a, you know, a big rate of increase per year. So in the chapter, we also talk about the regional differences, and so we show where the contributions are coming from for 2.6 and 8.5. You know, you can look at these at your leisure. We talk about how temporal variability in the ocean dynamics is dominating the regional patterns on the annual to decadal timescale, and how by 2100 we really do expect the anthropogenic signal to have emerged in most regions. We also look at the coastal locations. This has been taken beyond AR6 and works that Bob and others did with the NASA Sea Level team to produce this really nice tool. So, you know, what we talk about in the chapter is that by the end of this century, 2/3 of coastal locations will have a regional sea level rise within plus or minus 20% of the projected global mean sea level change. So I think that's quite a useful guide for policymakers to know that the global mean sea level, not for everywhere, but for many locations, it is really meaningful. But if people haven't looked at this tool, I definitely encourage you to look at it and to be able to look at the different projections at each of the tide gauges. And as obviously that's a great tool. There's also the interactive atlas, which I refer people to, where you can see the projections there for sea level, but also for a whole load of other variables as well. So I think one thing that is useful to think about is, or to look at, is how AR6 compares with what happened before. And so if we just look at the 2100s, and I think if you just even look at 8.5, which is this top panel in red, you can see that the main range of the projections is actually very similar in AR6 to what was projected in the special report and AR5. And what's really changed is the addition of the low confidence, which you can see. You know, we saw this in the structured expert judgment. We see it in some of the we see it in the Mickey projections. And so that's what's kind of been assessed here and taken through into our projections. And post AR5 scenarios, or projections which we would categorize as medium confidence processes, were again very similar to our projections in the medium confidence range. We don't have any low confidence for 4.5. 2.6, it's a very similar story as 8.5. So I just refer people to the definitions in AR6. These appear in the glossary. You know, and these are kind of terms which we grappled with, particularly in the summary for policymakers. You know, talking about are we seeing tipping points? We don't often refer to tipping points, particularly in the summary for policymakers. We talk about irreversibility and how the sea level change will be irreversible for centuries to millennia. And we talk a lot about low likelihood, high impact outcomes. which is outcomes where the probability of the occurrence is low or not well known, which is deep uncertainty. But if it happens, the potential impacts on society and ecosystems could be high. And so this is what we're trying to capture in this low confidence, deep uncertainty aspects of the sea level projections. So in this, in the high-end storyline, so we in box 9.4 in the chapter, we're trying to describe to a policymaker how this might occur. So there's these 5 bullet points I've tried to highlight from there, but you can read it in slow time. We talk about a strong warming scenario with particularly this low likelihood high warming scenarios that are discussed in chapter 4. So you see here, so in the equilibrium, climate sensitivity might have a range. If we if climate sensitivity is particularly at the high range here, you can see that we're looking at much warmer temperatures by 2100 than we would, for example, under the low ECS models. So that's very much the scenario we're describing. So 8.5 high ECS or close to 8.5. That around Antarctica, something like widespread ice sheet loss much sooner than expected. In Greenland, larger loss than is expected in some of the more standard projections with frequent melt events. And so in that box, we talk about how we might get up to an additional meter of sea level rise by 2100. And we also suggest that what is really needed to kind of keep track of this is to have some early warning monitoring, and perhaps somewhere like Thwaites Glacier, not surprisingly, would be a good place to for this to take place. So beyond the high impact, low likelihood scenarios, we also talk about extreme sea level flooding events. So of course, if your mean sea level has moved to be higher, not surprisingly, the flooding events which might have been once per century, we could be at those levels, once per year. That's what we saw in SROC, and really the message hasn't really changed in AR6. So we talk about things happening once per century in the recent past, occurring annually or more frequently at somewhere between 20 and 80% of tide gauges, or 60 to 80% of tide gauges by 2100. I also really like this figure, which was in chapter 12, where we talk about climate impact drivers. One of the climate impact drivers is about the relative sea level. So these are climate conditions that directly affect elements of society or ecosystems. And you can these are how many regions would be affected by this. And so you can see that well, for sea level and coastal flooding, there are a lot of regions that are assessed to be affected by these events. And in fact, the oceans and cryosphere overall are some of the really hard-hitting widespread events that we unfortunately expect to see. So just looking beyond 2100, I think most people are on kind of understand that it's not, will we exceed 1 meter, for example, 1 meter of global mean sea level rise, but when will we exceed 1 meter of global mean sea level rise? And so that's what this figure shows, that in some of the, in the low emission scenario, on average, we might not see that till 2200. For an intermediate emission scenario, it might be 2160. For a high emission scenario, it could be early in the next century, or in the worst case, even in this century. So what we didn't do, because we didn't think that we had sufficient evidence to be able to do this was to project a time series from present day right through to 2300. So we have the projections which went to 2150, and then we made an assessment at 2300. And the assessment at 2300, we took all the evidence that we had, and we basically put them in a P box. So we took the highest, which means the range covers the highest of the high to the lowest of the low. And so this is why you see quite large ranges for 2.6 and 8.5. We didn't feel that there was enough evidence to show this for other emission scenarios. And so, for example, if you compare that with something like the UKCP scenarios, you can see we have a much wider range. We also separated out projections from the marine ice cliff instability, and that's what shows this is shown in this dotted line here, that if the marine ice cliff instability becomes important, then we could be at even higher sea level rise. We could see even higher sea level rise by 2300. I put this here because I think probably we might kind of put another bottom line on these projections, because some work by Alex Nowles and co-authors, in their estimate was that historical missions up to 2016 alone would give at least 70 centimeters of sea level rise by 2300. So you could argue that that should be the minimum that's shown. There was only one study, so we didn't give this an assessment. It would be interesting to have more additional studies on this. So how am I doing on time? Badly. Okay, so just to say, people know this, that the projections that we made to out to the future are largely consistent with the paleo evidence from the last interglacial and the mid-Pliocene. So there is some paleo evidence to support these numbers, and that's also shown here. And so I think this is, although this shows much more than sea level, I think this figure from chapter 2's frequently asked questions is a really useful one to emphasize to people that the changes that we're seeing in sea level and beyond are really widespread, they're rapid, and they're intensifying. And just, a couple of things to highlight from the summary for policymakers related to sea level: that the changes are unprecedented over centuries to millennia, that many changes are now irreversible for centuries to millennia. We might be able to slow them down by limiting warming, but they're not going to go away. And that we can't rule out these low likelihood, high impact outcomes. And we have these real key uncertainties in the Southern Ocean and Antarctica. And that's what's said here. And then just to say about COP26, so, COP26 was, we were really able through a body called the Subsidy body for scientific and technological advice. So we had a session there where we were able, or several sessions where we presented the results from the IPCC report, and we took questions from the government delegates from the floor. And a lot of the questions related around the low likelihood, high impact outcomes. So not surprisingly, lots of support from the small island states for inclusion of these in the sea level projections. There was definitely pushback from some nations on the inclusion of these. And definitely questions around the early warning monitoring, where we should put that the monitoring to kind of have advance notice of this. The question of commitments I just flagged earlier, that was brought up. As I said, we only cite one estimate of this in chapter 9. Whether that's a question which is going to become more important on the in the policy world, I don't know, but it does seem to be a kind of a gap now when I look back in retrospect. And I think another question that comes really up from some of the outcomes of COP is, stabilizing the temperature, but what will happen if we overshoot? What are the consequences of that, particularly for sea level rise and some of these irreversible changes? Will we cross the tipping points? And so I really think this deserves some real thought by the ocean and cryosphere community and the sea level community. So some of my take-home messages I've tried to put in italics what I think some of the outstanding questions are. So it's obviously, virtually certain that sea level will continue to rise through this century and beyond. As I said, 3 degrees C at 2100 might not look so bad in 2100 for global mean sea level, but in the context of the extremes, 2300 perspective and deep uncertainty, I think that would be, very concerning. I wonder, and it's perhaps not feasible, but from a scientific perspective, it would not be nice to see a sea level target as well as a temperature target. It would be nice to be more sure about the what commitment we already have in terms of global mean sea level. We talk in the chapter about both Greenland and Antarctica contributing to deep uncertainty. I think we spent a lot of time on box 9.4 for one page, but it would be good if I think even there must be ways to improve the communication of this and to try and narrow some of the key regions and processes. Obviously, we, unfortunately, it seems certain that sea level will exceed milestones now. And we definitely need post-2100 scenarios to look at what will happen. But we also need to understand the implications of overshoots and tipping point and what that means for tipping points and irreversibility. Because of the regional impacts, we need to continue the monitoring. And we need to continue to communicate the regional impacts of far regions. As somebody who hasn't worked necessarily in sea level for, much before IPCC, it has surprised me how the general public aren't perhaps so aware that the implications of Antarctica, for example, in the UK. And extreme flooding events we expect to increase dramatically. And I think one thing we could flag moving forwards is that we really need to understand the impact of compound events in that kind of area. And with that, I will stop and just say many thanks to the whole author team and particularly the chapter scientists.
Thank you very much. That was a really wonderful overview. Gavin is clapping. So I have been holding off asking questions in the chat for the last couple of minutes, but I haven't forgotten them. So I think the first one comes from Gavin, and then we'll get through them.
Yeah, so you had and very appropriately, you had this like kind of, well, if everything goes to shit, then the high level numbers would be really much higher than we anticipate. And you specifically said here associated with Mickey. Now there's a lot of people that think that Mickey isn't a real thing and it isn't relevant, but that there may well be other unmodeled processes that cause the ice to be more sensitive than it would be otherwise, right? So yeah. I assume that you're just kind of using Mickey here as a stand-in for any of those other unmodeled processes that would cause models to be more realistic, particularly when it comes to the last interglacial or something like that.
Yeah, well, I'll let you discuss that with Robert DeConto, whether you think Mickey is a real process or not. But there's lots of uncertainties around the ice sheet processes. There's, and also the forcing, Gavin, as well, as I tried to highlight. So yeah, I talked a lot when we were at COP. I talked with Rob and Jonathan Bamber about what we would do to kind of try and reduce this range, and I think part of that has to be better understanding of the ice sheet processes and, you know, Mickey and other things that we don't understand.
Yeah, absolutely. Thank you.
Thanks, Gavin. Next we have Vivian, I believe. Would you like to unmute?
Yes. Yeah, you mentioned in quickly in passing about maybe we should be setting sea level rise targets as well as that for temperature. So could you please let us know how you would set such targets without really limiting temperature? I mean, how?
Oh no, I would definitely. Yeah, sorry, I didn't. I would definitely limit temperature, but what I guess I don't think this is going to happen because it's be too politically difficult, I suspect. But I just think when we look at scenarios, particularly overshoots, you know, you might say, oh, well, that's okay. We can get to a scenario where we end up at 1.5 by 2100. But how much you overshoot by and for how long could have a real implication for sea level. And so I'd like to, in that sense, at least from the scientists, I'd like them to say, okay, well, that overshoot, you know, we can overshoot and we can get to this, but this is what it also means for sea level. Does that make sense?
Yes. Okay. Thank you.
Next up in the chat, we have Harriet Morgan. Would you like to unmute?
Yeah, sure thing. Thanks. It's a bit of a complicated question, but so we have relative sea level rise projections in Washington State in the US, and we did a probabilistic framework for presenting the data based on COP 2014. And so we have our 1% and our 0.1%, and we're trying to sort of just, you know, naturally potentially answer the question of what we get all the time from the public is, well, how do your projections compare now that AR6 has come out? And so we're sort of trying to wrap our heads around this likely range for the low confidence scenario. And we're having a hard time interpreting that. And we're doing this comparison through that NASA localized sea level rise viewer that brings the relative sea level rise projections in. Mm-hmm. And specifically, we've also noticed that this low confidence scenario projection falls within the likely range for the normal confidence projections. And we're just having a hard time wrapping our heads around how that works and sort of doing this apples to apples comparison. And maybe this is sort of a more in-depth conversation that we can't have in a seminar Q&A, but I don't know if my question A makes sense, and if it does, if you could just speak to that a little bit.
So you're saying that the low confidence projections from AR6 fall within what you had as the normal confidence projections previously?
No, I'm saying
there's actually an overlap in our projections.
There's an overlap in your projections between the low confidence likely range and the likely range for the normal confidence.
Yeah, okay, well, I guess it's because it comes from the different sources of the, you know, some of the projections for the low confidence comes from the structured expert judgment. I think probably it would be better, Harriet, if we went away and thought about that and discussed it with Bob and Aimee and others, and come back with a better answer than what I could say now. I can imagine that is difficult to interpret, and happy to discuss it further. Great. If that's okay.
That would be wonderful. Thank you.
Just one thing on that though, like I said just to kind of flag again, I do think the facts thing for these regional projections for different areas, you know, having this framework available for people could be hopefully a good tool that people can use.
Great, thanks.
Next in the chat we have Shana Sadai. I'm not sure if it's a question, but if you have a question, please. It'd be good to hear from you.
Oh, sorry, I didn't have a question. I was just commenting when you were discussing the sea level targets versus temperature targets on your last slide. That was something I spent like the last 4 years thinking about. But yeah, thank you so much for your presentation.
Okay, well, it'd be great to see what you've written on that. I'd be interested.
Yeah, it's in review right now, hopefully coming out soon.
Thanks, Shona. Do we have any further questions from the group?
Well, since nobody else is here, so I mean, I think that AR6 did a much better job on this than the previous IPCC reports, and so I'm guessing that a lot of your kind of internal deliberations were kind of guided by the reaction that the previous reports had gotten and some of the criticisms that they'd had, and I think that you dealt with that. Do you want to like go into that a little bit more, or like where were the things that you felt previously IPCC had not really communicated things properly, and how confident are you that you did a better job this time? I think you did, but like I don't know.
To be honest, Gavin, I wouldn't have any criticism of what people had done before, because actually what's surprising is that most people on our chapter, all the people working on the sea level projections, were largely new to the process.
Right.
So it came with a completely fresh set of eyes.
Yes.
So that was interesting in itself, I think. And I think we wanted, I think one thing that was really important to us was to kind of to have something which was reproducible at the end. So sorry to keep banging on about facts, but that was really important to us, and we really wanted to kind of make this clarity between that there were processes which people didn't understand. And I think, you know, Bob and May came to a really good suggestion of separating out this medium and low confidence and putting it into that framework. So I hope people find that helpful. You know, I can appreciate that there may be some confusion about that. I think there are things we could have done better. Maybe, you know, it would have been really nice to have a complete time series from, you know, present day to 2300, but some things are just not possible. And our assessment was that we didn't think that was a viable thing that we could do with confidence.
Right. Okay, thank
you. Thanks, Gavin. We're just coming up close to noon. Do we have any further questions or perhaps final comments from anyone? Silence. It's very quiet. I suppose people might be worried or rushing to their next meetings and things. But yeah, thank you again ever so much for a fascinating talk. I really look forward to uploading this to the YouTube and making it available to the community later on. And yeah, hopefully we have you back. A few people are clapping, I see. Yeah, thanks everyone.
Thank you. Well, thank you very much for the invitation.
I hope you all have a great rest of the day.
Yeah, so thank you very much. Say hi to Chris for me, and we'll see you guys.
Yeah, we'll do. Yes. Soon. Yeah, well, and yes, and to you, hope for all's well in New York.
You know, it's also a sunny day here, so.
Oh, right. Well, it's not here, it's raining now, I think, so. Okay, all right, thanks guys, bye.
Bye, Helene.